All right, question 22, 24, 25, and 27. So 22, right, which isoelectronic series is arranged in order of increasing radius? Um, and isoelectronic series, they have the same electron configuration, and we know that cations are smaller because we've lost electrons from our largest orbitals, and we also cations, right? We have more protons than electrons, so we can pull those electrons closer. So we're going to be looking for um, honestly, I think right there is the only choice to start with because calcium 2 plus has lost more electrons than potassium. So that one should be first. Potassium would be next, argon's in the middle, and then anions. Anions are larger than the parent atom because we're adding electrons in and we've got more electron repulsion. The more electrons we add, the more electron repulsion, so it's going to be even bigger. So sulfide would be even bigger than chloride. So yeah, calcium, potassium, argon, chloride, and sulfide would be the correct order there. Um, Had a request, and again, with the direct comments, just put it in so everybody can see the question in the future, right? Um, All right, question 21. Of the following, which gives the correct order and atomic radius for magnesium, sodium, phosphorus, silicon, and argon? Let's see. We want to add in our periodic table here. So I've got magnesium, right? I've got sodium, I've got phosphorus, silicon, and argon. So we know, right, in general, as we go across the group, atomic radius decreases because of our nuclear effective charge, right? We're putting more um, protons in the nucleus. So in this row, sodium should be the biggest, right? Followed by magnesium, followed by silicon, followed by phosphorus, followed by argon. Because what's happening is, yes, we're adding more electrons, but we're also adding more protons, and those protons are going to pull the outer electrons closer and closer because the shielding is the same. Um, Yeah, for question 18, right? Orbitals being occupied just means there has to be at least one electron there. For a full orbital, right, we need to have at least two electrons total. But I want to get back on track for this video so I can get everything in it that I said was going to be in it. All right, question 24. All right, police radar detector operates on a frequency of 12 gigahertz. What is the wavelength in meters of this frequency? So we want to convert gigahertz to hertz, and then we can convert the frequency into the wavelength, right? Um, so 12 gigahertz is for every 1 gigahertz, we've got 1 times 10 to the 9 hertz. So I've got 1.2 times 10 to the 10 hertz, which is inverse seconds. So that's my frequency, right? We want to turn that into a wavelength. Well, we know speed of light equals frequency times my wavelength, and we want to solve for wavelength. So divide both sides by frequency. Frequency cancels out, and we get wavelength equals speed of light over frequency. So my wavelength equals speed of light 3 10 to the 8th meters per second over my frequency 1.2 times 10 to the 10 inverse seconds. Right, unit analysis, seconds cancel out, which is good, right? We're left with meters. Wavelength is in meters. They're asking for it in meters, so we don't need any unit conversions there. So let's see. 3 times 10 to the 8th and then divide that by 1.2 times 10 to the 10. And I get something like 2.5 times 10 to the minus 2 meters. So 0.025 meters. All right, for question 24. So convert frequency from gigahertz to hertz, and then we know that 1 hertz is equal to 1 inverse second, so we can directly take that into the frequency we need for this calculation. And then from there, it's knowing, well, I can relate frequency and wavelength together along with the speed of light. That's the equation we want to use to find what is the wavelength of this. They're asking for it in meters. We find it in meters right away. So yeah, it looks like choice D there is the correct answer. All right, question 25, right? Navy communicates with submerged submarines using a low frequency radio system. The signal has an energy of 1.42 times 10 to the minus 29 joules. What is the wavelength of this radio wave? So again, we want to get really good with identifying what equation do we need. Um, I would say energy equals Planck's constant speed of light over wavelength because this equation relates energy and wavelength. We're looking for the wavelength, so we can rearrange this to say wavelength equals Planck's constant speed of light over my energy. Wavelength equals Planck's constant 6.626 times 10 to the minus 34 joules times seconds. Speed of light 3 times 10 to the 8th meters per second. All over my energy 1.42 times 10 to the minus 29 joules. Again, units, right? We take a look. Um, Seconds cancel out when we multiply, when we divide, joules cancel out. We're left with meters. The question doesn't specify. Oops. The question doesn't specify, but hopefully it's asking for wavelength in meters. It should definitely say. And on the exam, I made sure to say what units do I want in my wavelength. All right, so 6.626 times 10 to the minus 34 times 3 times 10 to the 8th, and then divide that by 1.42 times 10 to the minus 29. And I get a wavelength of, yeah, a really big wavelength, right? Like 14,000 meters, right? Yeah, so like on the kilometer scale, which is huge wavelength, I get 1.4 times 10 to the 4 meters, right? So 14,000 meters, which, yeah, would be like 14 kilometers would be the length of one wavelength for that. All right, last question here, question 27. Correct, right? This is just telling you like they use this because the longer the wavelength, the farther it travels. The shorter the wavelength, the easier it is for it to get absorbed. And this is why like your Wi-Fi signal and things like that don't work well for long distances, right? Like you can't use your neighbor's Wi-Fi easily because really they don't travel that far. They get absorbed by different parts of your house. Whereas like radio waves, TV waves, that antenna, the station that's projecting that can be miles away because that energy travels a lot farther because that wavelength is a lot longer. And so it's not easily absorbed. It passes through material uh, much, much uh, more easily. All right. Question 27. And then, yeah, there's all the information you're going to have, the constants. Right. We did a question like this last year, And so it's kind of a holdover from that. We didn't really get into anything like that this question this year, but sure, it's dimensional analysis, right? We can work through this question. So how many photons of light are released from a laser? A zero point 0.5 watt red laser. The red laser runs for 10 seconds and it has this wavelength. And we know that 1 watt is 1 joule per second. Um, so, right, if we know that 1 watt equals 1 joule per second, well, we know that zero point 0.5 watts would equal zero point 0.5 joules per second. And we know that I run this for 10 seconds. So seconds cancel out. We're basically going to release 5 joules of energy. And what we want to do then is find what is the energy of one single photon to then help us figure out how many total photons would I need to make this energy. So we want to use energy equals Planck's constant speed of light over my wavelength. So energy equals 6.626 times 10 to the minus 34 joules times seconds. Speed of light, 3 times 10 to the 8th meters per second, all over my wavelength, right? My wavelength, 585 nanometers, right? We know in 1 meter, 1 times 10 to the 9 nanometers. So we divide by 1 times 10 to the 9. My wavelength is 5.85 times 10 to the minus 7 meters. Right? I'm going to guarantee someone tomorrow is going to do a calculation and they're just going to plug in nanometers as is and run it through. You'll get a number, sure, but it's not going to be the correct number. So just keep track of your units, right? All right. Multiply and then we divide by 5.85 times 10 to the minus 7. So I get the energy of 3.397 times 10 to the minus 19 joules. And this is joules for a single photon, right? So 4 per photon. Well, we need to make 5 joules, and we know I'm going to release 1 photon for every 3.397 times 10 to the minus 19 joules. So we want to divide. I didn't write that as neatly as I could have written that. All right, so 5.00 joules. We divide by joules, and we're left with how many total photons we need. And I think it's choice A. I think it is, all right, 5 divided by, yeah, 1.47 times 10 to the 19 photons, right? A large number, because photons, they're really small, their energy is really small, right? They're hitting us all the time and we don't feel it because they have incredibly small energy. And that's why we need an incredibly large number, right, to make up that 5 joules of energy. All right, any questions on those?